Hello everyone, welcome to our next lecture in the Material and Energy Balance class. Today we are going to be doing sections 4.7 F and G, so pages 150 to 161 in the textbook. Now this is the last part of our chemical reactions where now we're going to put everything together. So far we have looked at what happens when we have a chemical reaction going on in our system. Then we started talking about what happens if we have multiple reactions going on within the same reactor. Now we're going to put it all together in a huge process system, which is typically what you see in a chemical plant anyway. Because in general, reactors are not standalone units. You don't just have the reactor, you put feed in, you get stuff out, and that's all you do. Typically what you have is, and you see in any of our cases, we have our products that are together with other products or other things that are inside of that. So for example, we have our undesired products. If we have an unwanted side reaction, we have unreacted reactants that we need to get rid of. And so these unreacted reactants can also be recycled, and the unwanted products and inerts can also be purged from this system. So doing a very quick example, so let's say we just have a simple A converting to B in some reactor. In addition, we also have an inert in the system. Typically what you'll see is we have this fresh feed of A, and in this A we have an inert as well. It goes into a reactor where the A converts to B. So coming out, if we assume that we do not have 100% conversion of our A, we will have A and our inert coming out, and then the product B coming out as well. To get our product B, we actually need to separate out our B from the A and the inert. So typically it will go to a separator. Sometimes this could be a condenser where you will condense some of the product and maybe everything else remains in the gas and you can recycle that. Let's assume that this separator is not a perfect separator. So we are not going to perfectly separate all our B out as our product in stream 3. So we're just going to have some A and inert still left in our product stream in stream 3. And then we have this stream 4 that we'll essentially recycle it back in. So we're going to recycle stream 4 back in. What you'll notice is that in stream 4 versus stream 3, in stream 3 I labeled everything in terms of moles, and in stream 4 I did it the other way where I looked at the overall moles and then the mole fractions of that. Hopefully this will become clear why I'm doing this. Alright, so once we recycle that stream back in, the feed to the reactor is no longer the same as the fresh feed. In this case, our feed in the recycle stream has a bit of our product left because we are saying that this is not a perfect separator. So we have some product left, so the feed going into the reactor will have some of that B going back into the reactor. Typically what you see here is that we have this inert that's going to go through the system and it gets recycled. It's not going to get consumed, it's not going to get generated. So if we don't actually take out some of these inerts, we're going to start to poison our system as we accumulate more and more inerts within our system. So typically what we do is we don't recycle everything back in. Sometimes we will have a purge stream. This allows us to remove some of the inerts that we are putting into the system, and it doesn't just accumulate within our process. So this is just a very brief overview and example of what a multiple unit process with a reaction may look like. Obviously there are different variations of what this can be. So in addition to that, with a multiple unit process with reactions, we're going to come across two more specifications or two more equations. The first one, actually before we go there, I want to go back to the point of why I labeled stream 4 in terms of my mole fractions and my overall number of moles. And that's because down here you'll notice that when we have our stream 4 and then we put one to recycle and put one to purge, this is our splitting point. Going back to the lecture where we talk about what is the unique point of splitting points is that the compositions around the splitting points are the same, which means the mole fractions within these three streams are the same. If you had labeled it as the actual moles of A, B, and I, you are going to lose that piece of information. So around a splitting point, you want to make sure to label everything in terms of mole fractions so that in this case, you'll see that the mole fractions in the recycle stream and the purge stream is exactly the same as that of stream 4. Alright, now we can go to what I was trying to say here. We have two more equations that we need to talk about. The first one is going to be very similar to what we have already covered in a single standalone reactor, and that's the single pass conversion of our reactant. The single pass conversion of the reactant in this case is simply what we have talked about, the fractional conversion. So it is the input of A into the reactor minus the output of A from the reactor. That essentially means it's the A that is being reacted or consumed in the reaction. and you're going to divide it by the input of A into the reactor. So in terms of the variables we have listed, this would be number of moles of A in stream 1 minus number of moles of A in stream 2. And again, that's equivalent to the number of moles of A that has been consumed, divided by the number of moles of A in stream 1. So that's a single pass conversion. It looks pretty much the same as our fractional conversion that we have talked about before this. We can also define an overall conversion because now we are recycling some of our unreacted reactants back into the feed. The overall conversion of our reactant is going to be higher than that of a single pass conversion. So the overall conversion of A would be the input of A into the entire process minus the output A from the entire process divided by the A into the process. Putting this in terms of variables we have listed, what is coming into the process is NA in the feed. What is coming out of the process, in this case we see is coming out in two places, is coming out in our product stream, in stream 3, as well as our purge stream in the stream purge. And so you have two streams there, or two variables there from the output of A, from the process, and then you're going to divide that by the input of A into the process. So these two, again, are equations or process specifications we could potentially use to reduce our degree of freedom. Which systems will they affect? In terms of the single pass conversion, this is related to the reactor. In the case of the overall conversion, this will be related to the overall process. So before we start to do an example and look at a multiple unit example with reactions, one quick note, which is over the past few lectures, we have been so used to doing different methods, atomic species, extent of reaction, molecular species, and hopefully I've convinced you that once we have a reaction, it's going to be a lot easier to do the atomic species or the extent of reaction when you actually solve the problem. But now we're going to put in some units, for example, the separator, the mixing point, the splitting point that has no reactions. If that's the case, we need to go back to what we learned before we even talked about reactions, which is there's only one method to use, which is the molecular species. There's no extent of reaction to talk about because there's no reaction. You could do atomic species, but in general, what you're going to find if you end up doing atomic species, you're going to lose information. You're going to have not enough equations to actually solve the problem. So once we have units that have no reactions going on within them, you can only use the molecular species method, and that's the way to go. All right, so now let's start on our example. This is example 4.7-3 on page 155 of the textbook. And in this case, we have methanol that's synthesized by reacting CO2 with hydrogen. And you're given the reaction scheme right there. We have the fresh feed to the methanol synthesis process given with hydrogen, carbon dioxide, and some inerts, a very small amount of inert. The reactor effluent, so that whatever comes out of the reactor goes to a condenser, that's our separating unit. And it removes essentially all of the methanol and water and none of the reactants and inerts. The latter substances, so the reactants, the reactants and the inerts, are recycled back to the reactor, and to prevent the buildup of the inerts in the system, we have a purge stream that's withdrawn from the recycle. Then we're given more information about this process, the feed to the reactor, not the fresh feed, so this is the feed that is combining the recycle stream and the fresh feed. We're given the compositions of that stream with CO2, hydrogen, and inerts. We're given the single pass conversion of hydrogen in that reactor, and then we are told to calculate a whole bunch of different things with a basis given in there. The methanol production rate that we want is 155 kilomoles of methanol per hour. All right, so at this point, let's go ahead and go through the problem, draw the skeleton of the process, label the diagram, and see how we can do the degree of freedom analysis. So let's go through this problem and start by drawing the skeleton of the process. Then we're going to go back to the question, look at what information is given, and we're going to start to translate all the information onto this. So we're told that we have a fresh feed going into a reactor. So we have a reactor unit. And the reactor effluent is going to pass out to a condenser. We are told that there is a fresh feed that goes into this reactor right here. In terms of the condenser, so what a condenser does is it takes a gas and then converts some of that gas into a liquid. We are told that it can remove all of the methanol and water, so it condenses all of the methanol and water, and none of the reactants and inerts. So the reactants and inerts are recycled back into the reactor. And this stream in the very last line, it says it's recycled back to a reactor. It's going to combine with the fresh feed stream right here. Okay, and then to prevent inerts from building up within the system, a purge stream is withdrawn from the recycle. So we have a purge stream right here. So we have a feed stream. I'm going to start to label all of these. We have a recycle stream. We have a purge stream. And I'm just going to label this as 1, 2, 3, and 4. And like I said, I like to write the equation or the chemical reaction above that to remind myself about what's going on here. So we have CO2 plus hydrogen to give you methanol and water. All right, so now we have the skeleton of the process. Let's go back through all of this and start to label what information is given to us. All right, so going back to the first line, fresh feed to the methanol synthesis process. This is the fresh feed, contains hydrogen, carbon dioxide, and 0.4 mole % inerts. So we know that there is carbon dioxide, hydrogen, and we are given the inerts is 0.004. Okay, so we know the mole fraction of the inerts in that stream. The reactor effluent passes to a condenser, and methanol and water are going to come out down here. So the latter substances are recycled. The feed to the reactor, not the fresh feed, contains, we're given the mole fraction of this. So the feed to a reactor, we have the mole fraction. Carbon dioxide is 28%. Hydrogen is 70%. And our inerts is the remaining, which is 2%. Okay, so we're given that. The single pass conversion of hydrogen is 60%, so we can't do anything with that yet. And we want to calculate a whole bunch of different things, but we're given a methanol production rate of 155 kilomoles per hour. So this is what is given right here. This is our basis. We have one more piece of information, which is we said the condenser will remove all the water and methanol that we get and none of the inerts and the reactants. So the only other component in here is water. Okay, so now let's start to fully label this diagram. In this case, the one piece of information we are missing right here is the feed flow rate. Down here, we are missing the overall flow rate. I'm actually going to switch these. This should be 1, not F. Right here. And we're just missing the molar flow rate over here. Let's think about what is coming out of the reactor. Here, we know that we have, it says that we are given the single pass conversion of hydrogen, which means not all the hydrogen is being consumed. None of the reactants are going to be fully consumed, which means we're going to have carbon dioxide, hydrogen, and inerts coming out for sure. And at the same time, we're going to have our products. So now we have everything that's coming out of the reactor. This is going to go to a condenser. We know that all the methanol and the water is going to come out down here, which means these three are going to come out down here. And again, you see that I switched the way I labeled it. Down here, I'm labeling everything in terms of most molar flow rates of each component. Down here, I've switched over to the overall flow rate and the mole fractions. Again, it's because of this splitting point. We have a splitting point right here, and we want to make sure that we capture the information that the compositions are the same. All right, so we know we're just splitting these two streams, which means we have a recycle stream and a purge stream. And in the recycle stream, we have the same components. In the purge stream, we have the same components as well. And we need to make sure to capture that all the mole fractions are the same. So in general, what I do is I make sure to label that this is essentially equals to 4. And when I actually circle the unknowns, I circle these unknowns and not the ones for the recycle. So I'm not double counting or triple counting when I'm looking at these different streams. All right, so this is our fully labeled diagram. Just to double check, every stream has all the components that are accounted for. Now the next step, before we do our degree of freedom analysis, make sure to circle all unknowns so we can see where they are exactly at in the feed. We have here, this, and this. In the feed to the reactor, we only have one unknown. In the effluent, all of them are unknowns. In the product stream, we only have one unknown. Here we have all unknowns. And same thing down here. Like I said, you don't even have to write the recycle if you don't want to. You can just label it as 4 so you capture the information right away. But make sure to circle these right here. We don't know this. We don't know this. And those are unknowns right here. With this fully drawn and everything, we can look at the various systems that we have. What are the subsystems that we have? We have the overall. So in terms of the overall, what are the streams that will relate to the overall? We have the feed stream, stream 3, and the purge stream. That's our overall. We have our reactor. So when you look at the reactor as a different system, in that case, it's only just stream 1 and stream 2. We have our condenser. In terms of a condenser, we have stream 2, stream 3, and stream 4. And then we have our splitting point right here, involving these 3 streams. And then lastly, we have a mixing point. So we have 5 different units that we're going to look at. So now let's go ahead and look at the degree of freedom analysis that will give us an idea of how we can solve this entire big problem. So here's what we have drawn, our process flow diagram, fully labeled. We have looked at the different units, or at least identified the different units. We have 5 different units. We have our overall system, a reactor, a condenser, splitting point, and a mixing point. So the next step to do is to go through the degree of freedom analysis for each one of these units and use that to outline a strategy to solve for all of these unknowns within this problem. So let's start with the overall system, which is the big box. Note that for an overall system, in this case, the reactor is contained within that. So there is a reaction that's going on within the overall. So you would count the number of reactions as you would with just the reactor. So count every single reaction that's going on within this entire process. If we ever use the extent of reaction to solve the overall system, that extent of reaction will apply to that reactor unit as well. So let's start with the overall degree of freedom using the molecular species method first. In terms of the number of unknowns, we have 8 unknowns. Where our unknowns, we have 3 in the feed, we have 4 in the purge. We have 4 in the purge, 3 in the feed, and then we have 1 more in our product stream, which is the water. So we have these 8 different unknowns. The next thing we need to do is to add the number of reactions. So there is 1 reaction going on within there, so we have 1 reaction. The next thing we need to do is to subtract the number of molecular species. If you count all of them, you have 5. You have hydrogen, carbon dioxide, and inert, which are which is present in the feed. And then we have our 2 products, our methanol and our water. All right, the next thing we have are constraints. Constraints are if we label something in terms of mole fractions, then the sum of the mole fractions have to be equals to 1. You see that in our feed stream and you see that in our purge stream. So we have 2 constraints. That's all we have in terms of information. So 8 plus 1 minus 5 minus 2, we have a degree of freedom of 2. Let's double check this with our atomic species method. We have 8 unknowns. We don't add any reactions. We have 3 atomic species that are reactive, our carbon, hydrogen, and oxygen. 1 non-reactive molecular species, which is our inert. And then we have the same 2 constraints. You have the same degree of freedom of 2. I'm not going to go over the extent of reaction, degree of freedom, because in that case, all we are doing is we're going to split this out, the inert as a non-reactive. So we have 4 reactive molecular species, 1 non-reactive molecular species. Everything else, it will look identical to the molecular species method of degree of freedom. All right, so that's our overall. Let's move on to our next system, which is our reactor. In terms of the reactor, we have 6 different unknowns. We have 5 of them in stream 2, and then we have 1 in stream 1. So that's our 6 unknowns, not 5 unknowns. We have 6 unknowns there. Then we add the number of reactions, which is 1. We look for the number of species over here. Again, it's 5. We have all 5 of those species going through. Then we are given a fractional conversion of our hydrogen. So we actually have one specification, and go over how we write this in equation and make sure you understand what's going on. Since we have 60% conversion, 40% of what we put in stream 1 will come out in stream 2. So that's how we would write this specification here. So 6 plus 1 minus 5 minus 1 will give us a degree of freedom of 1. Double check it with the atomic. 6 unknowns, 3 reactive atomic species, 1 non-reactive species. We have the same specification. We end up with a degree of freedom of 1. With the molecular, the exact same thing. With the extent of reaction, we have the exact same thing as the molecular, except now we're going to split out the inert as well between reactive and non-reactive. So our reactor is 1. Let's move on to the remaining 3 units we have, the condenser, the splitting point, and the mixing point. Here's the condenser. Condenser has a lot of unknowns around it. We have everything unknown in stream 2, everything unknown in stream 4, and then one more unknown in stream 3. So that's 10 unknowns. There are no reactions in this case, so we are only doing a molecular species method. We're going to solve it with molecular as well. We have all 5 species within this condenser, and we have one constraint because in stream 4 we have labeled it in terms of mole fractions. And so now we have 10 minus 5 minus 1 is equals to 4 for the condenser. Let's move on to the mixing point. So the mixing point is where the feed meets the recycle to give you the feed into the reactor. Here we have 8 unknowns. We have 3 over here, 1 in stream 1, and don't forget the recycle, we have 4. Typically, I tend to label my recycle stream a little further away from the mixing point, and sometimes they have a tendency to miss out on that stream. But remember, the recycle stream is part of the mixing point. So in this case, we have 8 different unknowns. We only have 3 species. If you go over these 3 streams, there's no product at all in these 3 streams. So we only have hydrogen, carbon dioxide, and inert. 3 species, we can write 3 molecular balances. And we have 2 constraints. Sum of the mole fractions equals to 1 in the recycle and in that of the fresh feed. So we have 8 minus 3 minus 2. We have a degree of freedom of 3. All right, last one, our splitting point. Our splitting point is where our stream 4 splits into our recycle and our purge. So in this case, we have only 6 unknowns. You'll notice that in the streams of the recycle and the purge, I circled the mole fractions that are labeled as 4, not as the recycle or the purge. Because if you circle them as the recycle, you might triple count these mole fractions. When in actual fact, we already mentioned the fact that because it's a splitting point, the compositions are the same, and so those mole fractions should be the same. So we only have 6 unknowns. We have 3 of the mole fractions. We have each of the molar flow rates. That gives us our 6. Remember, in the splitting point, regardless of the number of species we only have 1 independent balance. All the species balance will collapse back into the overall balance. So we have 1 balance. We have 1 constraint, which is the sum of the mole fractions have to be equal to 1. And so we have a degree of freedom of 4. So let's recap all our degree of freedom. Overall is 2, reactor is 1, condenser is 4, mixing point is 3, and the splitting point is 4. So we don't have a degree of freedom of 0, which typically is a problem for us here. When this happens, one of the possible reasons is that we actually cannot solve this problem. This problem is underspecified. But in this case, it is not that. In this case, it just happens that we need to be more creative and think of a way of how we can actually solve this problem. So there's 2 methods we can do this. The first way is to look for a system that we can solve partially. Remember that a degree of freedom that is non-zero does not mean that you cannot solve for anything within that system. It just means that you cannot solve for everything that is unknown within that system. You might be able to solve for 1 or 2 of them, just not all of them. So is there a system where we can solve for 1 or 2 of those unknowns? And by solving just 1 or 2 of those unknowns, it drops an adjacent system to 0, and then now we can start from there, solve everything there, and then move on from there. So that's method 1, looking for systems that we can solve partially that will cause something else to drop to 0. The second method is to repick a basis. So in this case, we use the basis that's given in the question of 155 kilomoles per hour of product in stream 3, which is our product stream. Can we repick this basis? So let's consider that as an unknown. Repick a basis where around a system where the degree of freedom currently is 1. So if we have a basis over there, that drops it down to 0. And we can start over there. The only issue here is that we need to do one additional step once we finish solving, which is we need to scale it back up to this 155 kilomoles per hour. So looking ahead, as we are looking at going through these two methods, you will see that our reactor degree of freedom is 1, and this current basis that is not involved around the reactor. So if we had picked N1 or any of the streams or molar flow rates around the reactor, it would drop the reactor down to 0, and we can start solving from there. And that's what we're going to do in method 2. But for now, let's look at method 1, looking for systems that can be solved partially. It turns out that you could actually solve for the methanol balance around the condenser. Why? Because in the condenser, we know the methanol coming out is 155 kilomoles per hour. That's our basis. The only other methanol unknown in here is the methanol coming in, which is that in stream 2. So it's simple in minus out, and we can solve for that. With that, we will get our methanol flow rate that is going into the condenser that came out of the reactor. What does this do? By solving that unknown, we actually drop the degree of freedom for the reactor down to 0 because we have solved for one of the unknowns in the reactor. So now we're going to solve the reactor system. By solving the reactor system, we will get everything else. So we'll get all of these and stream 1. So we'll solve everything around the reactor. From there, let's look at where we can go next. By solving for N1, we would drop the degree of freedom around the mixing point down by 1 because it's involving the mixing point, but that still gives us a mixing point degree of freedom of 2, so that's not helpful. It turns out that by solving the remaining 4, in stream 2, you can see that the condenser degree of freedom will now drop to 0. So now we're going to go back to the condenser. In the condenser, first of all, we have only solved for one balance. Now we're going to go back to the condenser to get the remaining unknowns. So that will mean we're going to solve for everything in 4, and we're going to solve for the water that's coming out in 3. So now that we have solved for that, what is the adjacent system or the adjacent systems we can look at? We can look at the splitting point and the overall. In terms of the overall, we would have solved for the water and these components right here because they are the same mole fractions as that in 4. So we have solved for 4 different unknowns. We'll actually lose a constraint because this has been used. We'll look more into the overall at this point when we get there, but the overall will be the next one to go. Because if we look at the splitting point, in terms of the splitting point, we would have solved for all of these, and we would have 3 unknowns left, actually 2 unknowns left, but we only have 1 balance left, and so we actually still cannot solve for the splitting point. So we have to go to the overall at this point. From the overall, we'll get everything that's within the feed down here and the purge down here. Once we have that, we actually only have 1 unknown left, which is our recycle right here, NR. So in that case, you can either use any of the last 2 systems, either the mixing point or the splitting point, and you can get your last unknown. So let's go ahead and try this problem and solving it in the way that we just outlined down here. All right. The first step, solve the methanol balance around the condenser. Simple in is equals to out. The methanol coming out of the reactor is the methanol that's coming out in the condenser. It's 155 kilomoles per hour. Now it drops the reactor degree of freedom down to 0 because now this is no longer an unknown, which means we only have 5 unknowns. It drops it down to 0. How are we going to solve for this? We are going to solve for it by, remember, in terms of the extent of reaction, this is a non-reactive species. So we're going to write our 4 reactive extent of reaction equations, a non-reactive equation, so that will be our inert, and then a specification. So we're going to use these 5 different equations, or 6 different equations, to solve for our 6 different unknowns. Let's do the extent of reaction method in this case. Go ahead and try using the atomic species method and make sure you can get the same numbers as what we're showing down here. Here's our extent of reaction equations and the specification. So we have our 4 reactive species, methanol, water, carbon dioxide, and hydrogen. Those are our 4 reactive species, extent of reaction equations. We will actually need to couple that with our specification, as you can see in a bit. All right, so now as we look through these equations, you can see that we can now solve for our reaction unknown, our Xc, right away using equation 1, which is our methanol balance. So we have our Xc of 155. This allows us to put it into the second one that will allow us to solve for the number of moles of water that's being produced. And once we have that, putting it into 3 and 4 really doesn't do anything because we have still too many unknowns in here. So even though we know the Xc's, we still have too many unknowns in 3 and 4. So what's going on now? You realize that with our specification, it has the number of moles of hydrogen and N1 as our unknowns is the exact same as 4. So once we put in our Xc into equation 4, we need to solve equations 4 and 5 simultaneously. That will give us our number of moles of hydrogen coming out in 2, as well as the flow rate in stream 1. So once we have that, we can put it back into 3. Now that we know N1, we can put it back into 3, and then we can solve for our final unknown, the CO2. We have one more balance, which is our inert balance. We have not looked at the inert balance at all. These are just whatever that's reactive. So now we have one more equation, our inert balance. We have solved for everything at this point. In is just equals to out, and we can solve for our number of moles of inert. Okay, so now we have finished the reactor system. We are going to go back to the condenser. In this case, what you see that is we have solved for all 5 down here. So we are actually left with just 5 unknowns, 1 in stream 3 and 4 in stream 4. So this is now down to 5. We have already used up our methanol balance. That's the very first step that we did. So we actually have lost 1 balance. But we still have enough. It drops to 0. We have our 5 unknowns. We're going to solve it with our remaining 4 species balances and then our last 1 constraint, and that should allow us to solve for everything. So we're going to start with the water balance. That's the easy one. In is equals to out. So we know 155 kilomoles per hour coming in. We have 155 kilomoles per hour coming out. After that, because stream 4 is labeled in terms of mole fractions, you're starting to couple a lot of these unknowns. But because this is a non-reactive system, I said that in a non-reactive system, always think about doing an overall balance. So let's do an overall balance. It looks really complicated with a lot of different terms because you have 5 in stream 2, 2 in stream 3, and then 1 in stream 4. But if you look at everything that's going on in there, you only have 1 unknown left. So the overall balance will give us our N4, and you can calculate that right away. Once you have N4, you just have to do 2 more balances. We're going to do our hydrogen balance. We have 1 unknown left. It gives us our mole fraction. Do the inert balance, get us our mole fraction. We are done with our 4 balances. We have last equation we have is the constraint. We'll use the constraint to find our remaining mole fraction, which is the mole fraction of carbon dioxide. Okay, so now the condenser is done. Once the condenser is done, we said the next step is to go to the overall. How many unknowns do we have left in the overall? We have 3 in the feed. We have 1 in the purge. So we actually only have 4 left at this point. We lost the constraint because we already used up the constraint for stream 4. So we actually lost the constraint down here, and this drops down to 1. And so it would seem that we have a degree of freedom now of -1. We have 4 unknowns. We still have 3 reactive atomic species, 1 non-reactive molecular, and 1 constraint. It seems like it's going to be a -1. This turns out that it's not the case, and you'll see it as we solve it. This is one of the quirks of the atomic species method, which is sometimes the balances are just not as obvious of whether they are identical or they are independent. So if we solve the overall system here, and I write the carbon balance, so carbon coming in, we have carbon coming in CO2, we have carbon coming out in our product right here, and we have carbon coming out in our CO2 in the purge as well. So we have 3 different streams that have carbons going in and out of them. And we put in the numbers that we know, and we have 3 different unknowns in there. What you're going to find, and you can do it on your own here, if you write the oxygen balance and put in the numbers that you already have, it turns out you're going to get the exact same equation as what I've listed here in equation 6. And that is why we don't have a degree of freedom of -1. We actually have a degree of freedom of 0 down here, because writing the O balance and the C balance, simplifying it at this point, will give you only 1 equation. All right, so we have the carbon balance, 3 different unknowns, not helpful. Let's move on. Let's go to our hydrogen balance. And down here, we have everything that's listed down here with hydrogen. Put in the numbers that we already know. Once again, we see 3 different unknowns, so not helpful as well. And in fact, these 3 unknowns are not even the same 3 unknowns as the carbon balance. So let's do the non-reactive molecular species, the inert balance. In is equals to out. Here we have two unknowns. These two unknowns also appear in the carbon and hydrogen. So in this case, it looks like we have to use our constraint, which relates our two mole fractions. Now this is the case where we have to solve all four of these simultaneously. I'm not going to go through the math down here. The math will be posted online with the full set of solutions showing all the calculations. So try it on your own and do the algebra on your own and double check your answers there. But by solving 6 to 9 simultaneously, you can solve for these four unknowns. Once we have that, we only have one unknown left, which is our recycle. And that you can either do the splitting point or the mixing point. Is a simple overall balance for either one of them. In this case, I'm doing the splitting point, and you can find the remaining unknown. All right, so that is how we solve the problem in this case. The second method that I talked about earlier is to repick a basis around a system that has a degree of freedom of 1. And so the obvious one down here is to repick the basis. Rather than using 155 down here, we're going to pick N1 as our basis. All right, so by picking N1 as our basis, now you see that I have circled my methanol product as an unknown, but then now my N1 down here is 100 kilomoles per hour. How does this change the degree of freedom? I'm not going to go over it in detail, but anything that involves N1 will drop the degree of freedom down by 1. Anything that involves stream 3 will increase by 1. So the overall involves stream 3. It goes from a degree of freedom of 2 to 3. Reactor drops from 1 to 0. Condenser involves stream 3, so it goes up from 4 to 5. Mixing point involves stream 1, drops from 3 to 2. Splitting point is not affected at all, so it stays at 4. So now you have a nice system where you have a degree of freedom of 0. So we're going to start there. That will be the first one we'll solve. And once we do that, we're going to solve for these 5 unknowns down here. Those are the 5 unknowns around the reactor system. So what is the adjacent system? Well, the adjacent system in this case will be the condenser. By 5 unknowns, you can see that we have a degree of freedom of 5. That will drop the condenser down to 0. So we're going to solve the condenser after that. At this point, it's going to look very similar to what we have done in the earlier method. Once you have finished the condenser, you cannot go to the splitting point. You still cannot solve the splitting point. You have to go to overall. And once you have the overall, you'll have one unknown left after that, doing either the mixing point or the splitting point. All right. So I'm not going to go through the math of solving everything. Again, the math has been posted online with the step-by-step of what equations to write and what equations to solve and how you do it. I would strongly encourage you to try it on your own first before looking at the solutions. This is also the method that's presented in the textbook. So you can also read up the textbook solutions and you can see the same thing over there. But the one extra step we need to do after we have solved this problem this way is that we need to scale the entire problem back. Because remember, the question says we want 155 down here in our methanol product stream. What we have after solving this problem is 14 kilomoles per hour. So we need to scale our process back up to 155 kilomoles per hour. We're going to scale the methanol product by finding the scale factor. We want 155, right now we have 14, so we need to scale our entire process up by 11.07 times. So to do so, all the flow rates that we need, the fresh feed flow rate, the purge flow rate, and the flow rate into the reactor, we're going to multiply all of these by our scale factor 11.7. So those are the numbers on the left, are the numbers we did calculate using a basis of 100 kilomoles per hour in N1. Now we scale it all back up by multiplying everything by 11.07. These will be the numbers that will give us a methanol production rate of 155 kilomoles per hour. And if you double check these numbers, these are going to be the same as our first method where we didn't have to scale anything. We get the exact same numbers there. Just a quick note before we end here. When we scale something, the flow rates are going to be scaled, but the compositions are not going to change. So the mole fractions do not change in every single stream. All you need to do is to multiply the molar flow rates of all the streams that you have. All right, so that's all we have for this lecture where we are looking at multiple units with reactions. I've pretty much coupled an entire example within here. There'll be one more video example on a multiple unit with reactions example. So go ahead and look at that and to give yourself more practice. Work hard, be smart, and I'll see you next time.